Right. So now let's consider sort of a general class of second order discretizations. It's like of Hamiltonian systems of constraints, right? So this is a direct sort of symplectic discretization. Of a constrained Hamiltonian system. Right. So previously we looked at the shake and rattle methods. So it's like Endoza methods, which are second order accurate and symplectic. And so what we'd like to do then is to, in some sense, generalize that to a case where you have a constrained Hamiltonian system, but the Hamiltonian is not necessarily of the form of quadratic kinetic energy plus potential energy. All right. So let's see now. So let's consider a Hamiltonian system, a constrained Hamiltonian system. And we do this in terms of an augmented Hamiltonian, right, which we denoted by H tilde. And so this is just the unconstrained Hamiltonian. It's like plus a Lagrange multiplier term. Okay, which is sort of subject to the constraint that G of Q is 0. Right? And so what we're going to do is that we're going to assume that there is some sort of second order symplectic symmetric integration scheme for the unconstrained problem. So let us assume we have a second order accurate symplectic symmetric integration scheme. Sort of symmetric, say, one-step method. And let's just denote it by psi h. Okay. All right. Then psi h, of course, is a map from, it's like it's a map of the cotangent bundle of the full space. It's like back to itself, right? So it's not necessarily, it's like it doesn't necessarily respect, it's like the constraint, but you can think of it as a second order symplectic symmetric one-step method. It's like on the unconstrained problem on the full space. Okay, all right. For example, if the Hamiltonian, if the original unconstrained Hamiltonian separable, which is to say that you can write it as the sum of a kinetic energy part, which depends only on the momentum, plus a potential part, which only depends on the position, right? Then you could use, for example, Sturmer-Vallée. It's like as your second order symplectic symmetric one-step method. Could use Sturmer-Vallée. Okay. If it's not separable, then some other options include the implicit midpoint rule, right? So implicit midpoint. Rule, right? And what the implicit midpoint rule does is that it says that the solution at the nu times Zn plus 1 is equal to the solution at the O times Zn plus H times the vector field, okay, evaluated at the midpoint. Okay, so that's the implicit midpoint rule. Then the other possibility is the generalized leapfrog method. Okay, so the momentum at the half step is equal to the momentum at the original time plus minus a half step of the sort of the part of the vector field that's like associated with the momentum, right? Evaluated at the half step of the momentum and the original value of the position. So this is like a half step of a symplectic Euler type method, okay, in some sense. All right, and then you do a full step of the position, but which is obtained by some average of the vector field. So this is like almost like a trapezoidal kite thing. Because the momentum is at the midpoint, but the position is at the two endpoints, okay? And then the final step of the momentum starts from the half step and then gives you a half step of the vector field. It's like associated with momentum, but evaluated at the midpoint or the half step of the momentum, but the sort of the new value of the position. Okay, all right, so this is what is called the generalized leapfrog method. All right, so these, okay, so let me sort of just recap. So we need to have some sort of second order symplectic symmetric one-step method, which we denote by psi of h, and then some possibilities are if the Hamiltonian is separable, then you can use what is called the Sturmer-Verlet method, right? And if it's not separable, you can use the implicit midpoint rule, which is given here, or you can use this generalized leapfrog method, which is given here. Okay, in any case, once you have, it's like one of these second order symplectic symmetric one-step methods for the unconstrained Hamiltonian system, then what we're going to do is that we're going to take that one-step method and then modify it suitably so that you get something which is now consistent with the constraints. Okay, so I will just leave these two methods here and just delete the rest of it above this, and then state the method for doing this. So this is a second order sort of constraint preserving symplectic integrator. Okay, so it's Pn is equal, or Pn bar is equal to Pn minus a half step. All right, and as we saw, it's like with sort of the rattle method, right? There are going to be Lagrange multipliers which enforce both the condition that you know, it's like the new position is on the constraint manifold and that the new momentum is in the cotangent bundle, in essence. Okay, okay, so that's that. And then you do you apply the, unconstrained one-step method, if you will. Okay, so P bar n plus 1, okay, is equal to psi h applied to Qn P bar n. Okay, all right. All right. And then 0 is equal to G Qn plus 1. All right. So, so one way, if you will, to think about this, what you have so far, is that you are essentially modifying the initial condition in the momentum, you're imparting to this one-step method for the unconstrained problem so as to guarantee that the position at the new time satisfies the constraint that you're under constraint manifold. Okay, so that's one way to interpret this. All right, so you're tweaking, if you will, again, the initial condition for the momentum, right, so that the new position is on the constraint manifold. So now it's like Qn plus 1 is on the constraint manifold. It's like you now have to work on P at n plus 1. It's like to give you something which is on the constraint manifold. So, so in sort of a way which is analogous to this, right, you do Pn, well actually Pn plus 1, right, is P bar n plus 1. Right, so P bar n plus 1 is what you have gotten when you take this tweaked or correct position but tweaked momentum, take one step of the unconstrained one-step method, and then get the predictor of the momentum at the new time, but then you're going to correct that momentum at the new time so that again it satisfies the right constraints. Okay, so so again you have this half step. And then you have a multiplier now, which I associate with the velocity, but maybe let's call that the momentum term, right? All right, so this imposes position, this imposes momentum. Okay, and then the constraint is that you satisfy this cotangent bundle condition, which we talked about. Right. So this is correcting now the momentum at the new time, which had been obtained from this candidate value from applying the one-step method to the modified initial data. Okay, so all right, so this is the second-order constraint-preserving symplectic integrator. So some observations are that this thing is constraint-preserving. So this is constraint-preserving. Okay, symplectic, it's symmetric, and it's second order. All right, so in some sense what it does is that it takes some underlying psi h, which is a one-step method, which is symplectic, symmetric, and second order. So it retains all those properties, but by this appropriate, it's a correction, it also makes it constrained respecting. Okay, so as you might expect, it's like this is sort of motivated, if you will, it's like by the Rattle algorithm, and you can show that it reduces to the Rattle method. So it reduces to Rattle. Okay, for your usual Hamiltonian, which is 1/2 P transpose M inverse P, right, plus V of Q, and where this underlying one-step method is the Sturmer-Valet method. But in any case, it's like this sort of allows you, if you will, to generalize the Rattle method now to other classes of symplectic, symmetric, second order underlying one-step methods, and to Hamiltonians which aren't necessarily separable. Okay, so let me just stop here for now.